So it's time to begin. It's 11 o'clock. I'm glad to begin the morning section 3, July 18th, the ICBS. Now we introduce Professor Zhijian Ye to begin his talk about the effective and adequate theory of real computation with applications. Thanks.
Okay.
Welcome.
Thank you. Let me begin by explaining my title. The word effective, very often in recursive function theory and computability, it means just being recursive. But nobody uses it in that sense today, so I'm using it to mean if you design an algorithm, it's effective if you can really implement it and have the properties you claim it has. And to be able to implement ultimately means it actually can be converted, is Turing computable. Because today we define a lot of algorithms using abstract objects like real numbers, which you can compare exactly and decide whether it's zero and then branch. Most of those are not computable on a Turing machine, not without a lot of work. So effective means you want algorithms which really can be proven to be Turing computable. Adequate means, well, you need tools. In principle, you can very often prove that certain algorithms is Turing computable, but you may not be able to do that. And I'll give an example today about roots, a very famous algorithm about root isolation, finding roots of polynomial. That has been with us for 40 years, but we don't know how to implement it. No one has ever implemented it, okay? Effective and adequate theory of real computation. Okay, so let me begin. I'll have a lot of slides, so bear with me. The structure is that I have 4 parts. Introduction to theory of real computation, and then I'm going to go over 3 areas of application. Optimal roots, finding roots of polynomials, motion planning, planning the path of a robot, and Euler's method, tracking a homotopy path. And then I'm going to talk about how, using these as illustrations, how you can, from the algorithms you design, and you have to design it in a certain way, so that you can really get an effective algorithm out of it. And in all these work that I'm describing, we actually implement what we do, and they're all effective in that sense. And I will conclude. So 4 parts. So you all are familiar with the construction of the real number line. It's the foundation of modern analysis. You use Dedekind cuts or Cauchy sequences. But is this the full story? Some of you probably know that it's not the full story. A few years ago, I was very struck by a sequence of quotes from John Bell, his book on A Primer on Infinitesimal Analysis. So he quotes from Aristotle, Leibniz, Kant, all philosophers, because philosophers were trying to understand the concept of the continuum, the continuous space, versus atomic or point space, right? And there's a lot of debate. The atomic view didn't win until much, much later. But the continuum is still there. So you can read the quote for yourself, but let me just read the shortest one. Leibniz, a point may not be considered a part of a line. You say, what? That's what I'm told. A line segment is a sequence of points. So obviously, Leibniz don't quite agree with you. And then there are famous mathematicians, Weil, Poincaré, Brouwer, René Thom. Again, I'll quote the shortest one. A true continuum has no points. So continuum is usually another name for the real number line. Okay, or you can define it topologically, but okay. And if you think deep about this, you'll realize that yes, these points are true, and you can see ideas like that from infinitesimal analysis, from measure theory, where you only can work with certain nice sets, not arbitrary sets, and basically they're trying to capture a continuum. And for us in interval, you know, there's a world of computing called interval arithmetic, computing with intervals, as if you're working with numbers. To me, that struck me as interval methods are absolutely essential to everything we do if we're going to design effective algorithms. So keep that in mind as I talk. And then the other quote I have is from Blum, Tucker, Shoup, and Smale. In 1996, they issued a manifesto. Manifesto means a declaration, like Marx has a manifesto, right? Workers of the world arise kind of thing. So this is what we have to do. And they were calling for a foundation to the theory of modern scientific computation. And they said that, well, the Turing model is not very good. And I want to point out that, say, at the same time, more mathematical, less dependent on logic. So we propose a theory of real computation. But actually, the theory that the model they propose is just what theoretical computer science call the real RAM model, random access, where you can manipulate real numbers as individual, solid, atomic wholes exactly. You can check whether a real number is 0 or not and branch. They also quoted John von Neumann, who complained about the theory that's being built around the time in the 1930s, 1940s, around Turing machines, complaining that formal logic is too rigid, all or nothing concepts, and it has very little contact with the continuous concept of the real or complex numbers. And so this was quoted in that book. And let me put it this way, you're going to hear the word soft a lot of times in this talk. And this is my way of talking about this kind of ideas, soft as opposed to hard, okay? We'll see example. So somehow the real world is softer than what mathematicians and logic makes it out to be. So for those of you who have a complexity theory background, theoretical computer science, where you study theory of computation, complexity theory, P, NP, completeness, and so on, complexity theorists have been very puzzled. They have tried to create a theory of complexity for the numerical analyst, but the numerical analyst, NA, always ignores them. So here's a imagined conversation, CT, complexity theorist. Here's a generic task of numerical computation. Given L, a natural number, and a rational expression, oops, I hit the wrong thing, did I? What did I do? Sorry, I blew it. Oh, my computers, maybe you can you try to keep it alive? I'm not quite sure. Okay. And I give you a rational expression which represents a rational number. I want you to compute an L-bit binary representation of P over Q. So an approximation, L-bit, correct up to the last bit. Last bit, you can round it up or down, doesn't matter. Theorem. Well, this problem has complexity between P/poly and P space poly. Now, if you know something about these two classes, the /poly means you're basically turning the complexity class into a non-uniform class. So actually, that complexity is very high. It's amazing. The numerical analyst says, I'm not impressed. That's not our problem. But why? It has little to do with the problems of numerical analysis. Ghost of von Neumann. Remember the quote I gave of von Neumann? That's exactly what they're saying. Okay, we can show you that complexity depends on the condition number K. So numerical analysts analyze condition numbers a lot to understand their algorithms. But usually their answer to condition number is say, well, if the condition number is infinite, they just throw up their hands and the algorithm doesn't work anyway. Okay? So it's still no good. K may be infinite. And for theoretical computer science, we are interested in algorithms that doesn't blow up, even if k is infinite. And you'll see how we deal with that. So one solution to this is something called smooth analysis of Spielman and Tang. But the solution that I'm proposing is called resolution exactness, which is predicated on an extra resolution parameter. So whatever algorithm you have, I give you an extra parameter as input. You specify that epsilon positive, and we will compute something to that precision. So, oh, that's easy, isn't it? Because if every arithmetic step is computed to certain epsilon, well, that's, of course, it's not at that level, not at the level of every arithmetic operation. That's already been achieved by your hardware. IEEE arithmetic, every operation is correct until the last bit. But if you sequence a bunch of operations, the error grows. And at the end of a long sequence, you get nothing. Every bit in your number is garbage, nonsense. And this is not easy, and you'll see why it is. But I hope I'll convince you that this is a very good solution to all these problems. And I've been working on something I call exact geometric computing, EGC, for quite a while. We did a core library, and the fundamental insight that I had in that period was that, you have to decide zero, because all geometric phenomenon depends on zero. Whether your concept of a line, if you're on a line, your equation evaluates to zero. If you're not on a line, it evaluates to positive, it means you're on the side of the line. Negative, on the other side of the line. So deciding the sign of a number is absolutely essential in all geometric computing. And in exact geometric computing, it says, just make sure your sign is always correct. You don't have to compute with exact numbers, but make sure it's correct sign. And to a large extent, we can do that for algebraic case. And I wrote a paper in 2008 called Theory of Real Computation According to EGC. The drawback it is a beautiful theory. I still love it. And to do this kind of work, you have to basically determine root bounds so that you know how to stop. Because the problem of deciding whether a number is zero, I call it the numerical, it is the numerical halting problem. If it is not zero, and we always assume whatever quantity you have, you can approximate to arbitrary precision. Well, if you compute it high enough precision, you'll see that it is not zero. And you can tell whether it's positive or negative. But if it's really zero, you don't know where to stop, right? There's a halting problem. Just like the Turing halting problem, if it's zero, it's basically undecidable, not computable. But if it's, so one side is easy, the other side is hard, one-sided. But it's different from the Turing halting problem. But really, most of the work in computer and numerical algorithms are outside the realm of such approaches. So about 10, 15 years ago, I switched. And one thing that I realized is that we don't really need exact computation. If you look at the physical constants, all the physical constants are known to about 8 digits of accuracy. Constant of gravity is the worst. It is in the Guinness Book of Records. It's the worst constant. We only know 4 digits of accuracy. And speed of light, is perfect because that's by definition, the definition of the constants. So exact algorithms may not even be meaningful in the physical world, okay? And I work on robotics. Everything in robotics is approximate. Even the shape of the robot. When you hit the map that you have of the room, everything is, what are we talking about exact algorithms? So I became convinced that this is, I should move away from exact computation. I'll skip, I need to really speed up. So we'll develop these ideas. If you look at the history of theory of real computation, there's quite a lot of theory out there. And I criticized all that in my 2008 paper. And I realized that this is all building theory from top down. from the mathematics, their understanding of real numbers, you try to build a theory of computation. That's not the right way to do it. So I'm sort of insistent that I built my theory from bottom up by looking at hard, difficult problems that we don't really know how to solve properly and see what are the techniques we need. So here's the first of the problems, optimal roots. And in each case, I have two parts. 2A is about the, well, yeah, A is the first problem. That's A1, A2. I'm sorry, the structure of my talk got a little bit complex. So we all know FTA, Fundamental Theorem of Arithmetic, basically going back to Gauss and even earlier, that says that if you give me a complex polynomial of degree n, it has exactly n roots, counted with multiplicity because you might have multiple roots. I call FTAA. The second A here is algorithmic, Fundamental Theorem of Algorithmic Algebra. The algorithmic part means the computational aspect of computing roots. And basically, the whole subject began in 1981 from Schoenhager, whose monumental paper has never been published, but widely cited. Beautiful work. And then Victor Pan and other people built on it. So by the time of, about 10 years later, we all basically believe in this result. There exists a Turing machine to isolate all roots of a polynomial f of x with dyadic coefficients. Dyadic just means floating point numbers, right? The denominator is a power of 2. A rational number whose denominator is a power of 2. And if f, so that's how we get approximate algorithms. That's how we get approximate polynomial coefficients by using dyadic numbers. And then if the polynomial has degree n and the coefficients are L-bit integers, then the complexity is about the soft tilde, O tilde. The tilde means you're hiding logarithmic terms, n squared L. And basically this is optimal. You can construct counterexamples. And we say near optimal because there are special cases where you can break this. But this is basically the correct picture. So we believe that. We know it can be done. It exists. But no one could get an effective algorithm, implement this. So I have to just very quickly mention what we mean by finding the root. And I called it a benchmark problem. Benchmark because it's a complexity benchmark. Complexity theorists like to have benchmarks. They say, what's the complexity of this problem? Well, to find one root, to find all the roots, to find all, whatever. They're all different computational problems. So the simplest problem to say is compute all the roots. And that's what I call the benchmark problem. And that benchmark problem, we understand the complexity very well, according to this theorem, basically n squared L. We like to know benchmark complexity results because once we know that this is basically that, then we move away and use those algorithms without worrying about it. It's like today you use big integer algorithms to multiply, to divide. You know it's basically optimal. You use big integer computation in GNU or Java. They implement nearly. Then we move on to the higher, more difficult problems. And root isolation now, in some sense, has joined that bunch of fundamental operations that we assume in scientific computing. But there are a lot of other things, of course, we don't know. And while numerical analysts usually talk about numerical approximation, just says to compute to epsilon. But if two roots are very close, are closer than epsilon, you really can't distinguish them. You don't know, is it to the left or right of each other, or are they really the same thing? So it's too weak. And people in computer algebra and exact computation like this, that I think is an absolutely correct notion called root isolation. To isolate a root means to give me a disk that contains that root and nothing else. Well, of course, if there are multiple roots, you have no choice, but you have to tell me the multiplicity. Okay, that's called root isolation. And once you have root isolation, well, if you really want to refine it to arbitrary precision, that's actually fairly easy. So we don't even talk about that. So this is the key problem. It's a topological problem, getting the correct topology of the roots. And then you can also generalize what we're doing to clustering. I won't have time to talk about that. So the twists and turns of FTAA from 1981. So the basic story that I want to tell is that now that we know it exists, how do we turn it into an implementation? How do we make it effective? And for a long time, it wasn't, well, whatever people, well, there are two classes of algorithms implemented in the real world. The numerical analyst that doesn't guarantee anything. Most of the time they are good, they're very fast, but they don't guarantee they're correct. Versus the certified or guaranteed or validated algorithms, which people in computer algebra and algebraic computation like Maple, Mathematica, they like to have certified algorithms. And all the certified algorithms are based on subdivision. Basically, if you want to find real roots, you subdivide, 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 using Sturm sequences, using Descartes' rule of sign. They're certified, but if you look at the complexity, they're always about order n less than the optimal. But finally, in 2016, this was broken. Finally, using subdivision, we can reach this kind of methods. And 2018, I'm involved in this second work. Even for complex roots, we can do it. And the two algorithms are very different. Real roots and complex roots, fairly different techniques. And surprisingly, both these results of subdivision do not depend on Schoenhager's technique that he introduced in 81. Because everybody thought, you can't reach optimal without using the splitting root circle idea. The splitting circle idea simply says, if you give me a polynomial, the first thing I do is compute two polynomials whose product is equal to your original polynomial, but they contain about between 1/3 and 2/3 of the roots, so that you can do divide and conquer. But these techniques are independent of that. So at this talk, we'll look at the soft ingredients at a high level to see how we achieve all that. The first idea is what I call well-isolated. I'm going to use it again in the Euler method at the end. So a complex disk delta is called well-isolating if the number of roots in delta, of the polynomial, of course, is equal to the number of roots in 3 delta. You take you expand it 3 times, and you don't get new roots. They're equal. And so this is well isolated. Any set of roots inside some delta is called a cluster. But if it is well isolated, then we say the cluster is natural. So for instance, suppose you have these roots, red, blue, green. Well, the red roots form a cluster because there's a disk containing it, right? But it's not natural. Any disk containing those 2 roots, if you make it 3 times bigger, will include the green root, right? So it's an artificial cluster. But this blue cluster is natural. If you make it 3 times bigger, it will not contain any new roots, all right? And we like natural clusters. There are 2 very simple reasons for that cluster theorem. Any 2 natural clusters, they're either disjoint or one is containing the other, right? They cannot just intersect partially. And therefore, any degree n polynomial has, well, in general, they have n cubed clusters combinatorially, but there are only less than 2n natural clusters. You can form them, put it into a tree, actually. Very nice cluster tree. So we work with these kinds of things. And how do we locate clusters? Well, there's a very famous test called Pallet from 1831. He says, basically, I'll make it simple. So if you're giving a polynomial and a disk, for those of you who are familiar with this sort of things, this is basically taking the polynomial, shifting it to the center of the circle. It's called Taylor shift. And then you take the kth coefficient of the shifted polynomial and take its absolute value, r to the k divided by k value. And all the rest, you put it, sum all their absolute value. And if this guy is bigger than all these guys, then you say there's exactly k roots in that disk. Exactly. So this is a very famous result. Then the number of roots is exactly k. But if it succeeds. So I want to make a clarification here. What I call a test, we're all familiar with predicate. In logic, we have predicates. A predicate is either true or false. If the predicate is true, not true, then it is false. If it's not false, it is true, right? There are only two values. Test is different. A test either succeeds or fails. If it succeeds, it has the property you want. If it fails, you don't know anything actually. All right? But what we really need in soft algorithms is partial converse. So if it fails, then I know something. Or another way to put it, under certain condition, you must succeed. All right? So here's, you can do the analysis and see that if you take the disk, shrink it by 1 over 11 times n, make it very small. And if all your roots are in there, and you take the disk and expand it by n cubed factor, and you don't get any new roots, then palette will succeed. So wow, that's not very helpful. Not very helpful. Computationally, how can you use this? All right, let's go on. Well, there's a technique called Graeff's acceleration, where you take a polynomial f and you transform it to another polynomial, f to the 1, and then you can transform it f to the 2 and so on. And the point is that if you do it n times, capital N times, then the roots of this polynomial are exactly the original roots, but raised to the power 2 to the n. So you're growing exponentially fast. So what does that mean? If you have a root who is not on the unit circle, but say inside the unit circle, you shrink very fast towards 0. And those that are outside the circle will expand very fast away from 0, right? Very fast. And so we work with that polynomial. This is a, and so here is the geometry of what we really see. So this is the green circle is your original delta, and the maroon or reddish brown circle is the smaller one, 1 divided by 11n, and this yellow circle or disk is the 64n squared, much bigger. And we know that all the roots, there are no roots in the green and yellow region, no roots. But if you use the Graeff expansion, we can turn into a predicate in which now it's, if you know, usually when we do subdivision, we subdivide boxes. We don't use circle geometry. You can subdivide circles, not easy. But you subdivide boxes. So if you have a box B, you apply this test to this circle, this green circle, slightly bigger than the circumscribing circle. Then if there are roots in here and no roots in this yellow and green region, then it will succeed. And if it fails, then, well, then you know there are actually roots somewhere in here. So this is our main predicate. And I call it soft because it's not like a sharp boundary. I think I'm probably running out of time here. I'm not very good at keeping time here. And then we are not done yet. The way I describe it, all the arithmetic has been done exactly, but you really want to do it approximately. And this is what I call soft evaluation. And, well, at the end of the day, this is what you get. And using this, now you have something you can really achieve the kind of near optimal isolation. How much time do I have? Huh? How much time? Can you drop a sign and tell me 10 minutes left? Huh? 30 minutes. Okay, remind me again. I have to go faster for sure. I'll talk about motion planning. So motion planning is something in robotics. Assume that you want to move from point A to point B, and you want to avoid obstacles. And the obstacles, let's say in this picture here, are these two green, this pink rectangles, and A is this point, B is this point, and there are of course three different paths, three different topologically different paths. This may be the fastest. This one may be the safest because it's as far away from the walls as possible. And this one is perfect circle, so it's smoothest, whatever. So you can have all kinds of criteria. But in path planning, you usually just make the simplest problems. That exists a path, just show me any path. Okay, we don't talk about optimality. That's a separate problem. And you know the map, and you know where you are in the map. Because there are other versions of this kind of problems where you don't know. You have to locate the map. You have to locate your environment and all those things. So that's much harder. And only kinematics, there's no dynamics in here. And there are basically three approaches that has been around since the 60s. In AI, they studied, they call it find path problem. But in the 80s, people started to look at the geometry more closely. AI, of course, just turned it into a graph search. Discretized the problem to a graph search. Early AI is all graph theory, actually. At that time, we were just learning about graph theory and fascinated by graph search, exhaustive search. But this is introducing more geometry. And then there's this exact approach by Schwartz and Charia, my colleague at Courant, who worked on this. And then there's sampling approach. And today, all the robotists who implement these algorithms all use sampling because it's very easy, very fast. You just do random sampling of the space. And this is a quote from a famous textbook. These are all the different kinds of sampling methods. PRM, EST, RRT, SRT, and so on have changed the way that path planning is performed for high-dimensional robots. They also paved the way for the development of planners for problems beyond basic path planning. This is a book by Choset and 6 other authors. But the problem with the sampling method is if there's no path, it doesn't know it. It doesn't have any way of stopping. You just say, time out, I've searched for a path for 2 days, I couldn't find, stop. But we want a way to stop when there's no path. So I don't want to go into the details, but just to remind you, if you already are familiar with these terminology. So let's assume you have a rigid robot R0, which is in R2 or R3. Let's say R0 is a triangle. And then configuration space is basically the parameter space of parameterizing its position. So if you have a robot, then C space is basically XY, which is R2, and an angle that will tell you how the robot is. And basically, there's a map. I call it a footprint map that maps configurations into a subset of Euclidean space. It tells you where the footprint of the robot is. Where's the robot standing, right? Standing here, standing here, different footprints. You look at the footprint. So that map is inherent in the definition of the robot. And then the obstacle set, let's assume it's polyhedral set, it's a subset of RK. And then free space are just all those configurations where you're not hitting any configuration or obstacles. You're free from the obstacles. And paths are just continuous functions that maps you in the free space. And the clearance of a path is just how far what's the closest you approach hitting the obstacles. Okay. So here's the path planning problem according to exact path planning. You're given the obstacles, alpha, beta, which are the start and goal configurations, and you either output a path, if there's one, or you output no path. That's it. Well, this is a difficult problem. It requires exact computation. And the algorithms are very hard to design if you really want to worry about all the degenerate cases. But what we propose is something called resolution exact. Resolution is just, I give you omega, alpha, beta, S before, but now I give you an extra parameter, epsilon, and I call that the resolution of your resolution is positive. So sometimes I get epsilon exact rather than resolution exact. So, and again, you output no path or you output a path. And it has to satisfy these two conditions. Your algorithm has a constant k, which is positive, say k greater than 1. And if there's a path of clearance k times epsilon, you must output a path, okay? If there's a path that's so wide and your robot is so small, you say no path, that's terrible, right? To make it things, just think of k equals 2. So if there's a clearance 2 epsilon, you should find a path. But if there's no path of clearance epsilon over 2, then you must output no path. So no path actually means something. It's not because you ran out of time looking for it. The point is that if the clearance is between epsilon over 2 and 2 times epsilon, actually I don't care whether you output path or no path. Both are okay. Okay? If I'm concerned about it, I can change my epsilon. I can make it smaller, I can make it bigger to get a different answer. Okay? So this is the concept of resolution exactness. And you can already see this will now break out of the zero problem. We don't have to decide zero to solve this problem. And basically, for interest of time, I'm going to just tell you that we have been working on this for over 10 years, and we have designed all kinds of robots, implement them, do experiment, compare with the state of art, and we beat them. Okay? Beat the sampling methods and all those things, which are much weaker. They don't have a lot of guarantees at all. If they find a path, yeah, they found a path, but even that is not so clear. And our latest challenge, my PhD student here, Chee, is finishing up his thesis. Robotics has this challenge for a long time to design an explicit algorithm for a 6 degree of freedom robot. So in 3D, a rigid body has 6 degrees of freedom, 3 degrees of translation and 3 degrees of rotation. And you want to implement it. Rigorous, complete, implement. We are almost there. We're in the process of implementing. We have designed it. This has never been done. This has been a challenge among theory people for a long time. So I'm going to just very briefly tell you what is the subdivision paradigm. So subdivision, what we're subdividing is not physical space, but configuration space. So the configuration space has to be split. So in this case, R2, you know how to split R2 boxes. But a circle is a little bit, but circle is very easy, basically a line. So no problem, you can split it. But the real challenge is in SE3, which is R3 cross SO3, the rotational group. For those of you who know SO3, you can view this as 3 by 3 orthogonal matrices representing rotation, or you can represent them using quaternions, using only 4 numbers, really 3 independent numbers. In fact, you will use the quaternion representation to represent rotation. But this is non-Euclidean. How do you do subdivision here? So that is the challenge, and to design the data structure and everything that works. So I think I'm going to just illustrate it for this case. You're trying to find a path for the robot in this square here. And the robot is a disk. Here's a disk here, start. And it's trying to move to a final alpha to beta. And the obstacles are some polygons, a bit hard to see, triangle, rectangle. And it turns out configuration space for a disk is so simple that it's the same as the physical space. That's about the only time you get that, when your robot is a disk. And so each of these boxes represent a configuration box. And we color it green, yellow, or red. Red means that every point in every configuration in there is not free. Green means every point here is free. Yellow means, well, there might be some free, not free, but I'm not, or maybe my approximation is not good enough. So it's yellow. I'm not so sure. All right? So green is definite. Red is definite. Yellow, we can further subdivide and get more information. Right? So this is how you do subdivision in 2D. Very simple. Here's 3D. Now the robot is a triangle, so now you have 3 degrees of freedom, but I'm still representing it on 2D. So you can think a third dimension coming out of the wall, and the third dimension is the angle. So we have to blend the colors. There's still only, every box is either yellow, green, or red, but if you have several boxes, you can blend them into some intermediate colors, okay? So, and higher dimensions is much harder to represent or to visualize. But it's very helpful to visualize how these algorithms are doing. So we basically every box in your configuration space is classified into one of 3. Green means free, means every point in there is free. Stuck means every point there is not free. Mixed means there's some free, some not free. And gray means, oh, it's smaller than epsilon, okay, you can throw it away. All right? And because we're doing resolution exactness, that's why you can do that. And basically, the subdivision, what I call soft subdivision search, SSS, is this loop, this simple while loop. While the queue is not empty, you just keep taking a box. The boxes that are yellow is put into a queue, and you take it out, you split it, and then classify them. And if it's green, you're done. If it's red, you're done. If it's yellow, you put it back into the queue. And when there are no more boxes in the queue, no path. You up and no path. And you prove that this is correct. All right? Questions? Okay, I'm going to skip all this. The point is this. Where's the softness? As I said, what I'm really trying to teach you or convey to you is the idea that everything we do is not hard, not exact arithmetic, but all soft. So when we classify a box into free, stuck, or mixed, that's clear. The meaning is clear. Mathematically, it's clear. It's exact. What I want is soft classification. So C of B is the classification of a box. C tilde of B is also a classification, but it's an approximate classification. This approximation is conservative. It means that if it says free, if it's not mixed, then it's actually correct. If it says green, it really is green. If it says yellow, red is really is yellow. But if it says yellow, it just means it doesn't know. All right? And it's convergent. If the boxes converges to a point, then in the limit, the classification will converge to the correct answer at that point. So we call that a soft predicate, soft version of C. And we have, and there are challenges, there are geometric challenges to do it for various kinds of robots. We did a 4th degree link robot, very interesting topology. But the current challenge is this, what we call SE3 robot, which is a 6th degree freedom robot. And as usual, in theory, we always try to design robots in the simplest shapes, like a disc, a triangle, a rod, a ring, and so on. And in 3D, the simplest for us is to define a triangle like this. This triangle is our robot. We call it a delta robot. And here's some visualization. By the way, there's a poster. Chee has a poster out there, well, in A2, describing this work. So you can talk to him if you're interested. And our SSS technique is remarkably versatile. You can fatten your robot. You can make unions of complex shapes, none of which exact algorithms are capable of doing. In an exact algorithm, every time you change something like that, you have to design a completely new algorithm. And another challenge we have is how to do subdivision in SO3. So viewing it as a quaternion is really the surface of a 3-dimensional sphere. which is the boundary of a 4-dimensional ball, and if you project it onto the boundaries of a 4-dimensional cube, then the cubes there are 8 3-dimensional cubes, but the opposite faces cubes are the same, so we are down to 4 cubes. So SO3 can be computed by looking at the adjacencies among these four cubes, and we have to deal with that. And then we have to produce a chart, a subdivision atlas, like in differential geometry, you have charts and atlases. We have to do that and figure out how to get information out of our subdivision. So how am I doing? 15 minutes, okay. Okay, now the third area is getting closer to something that I'm in the midst of working very hard on, Euler's method and adaptive corrector. So I think most of you have seen Euler's method, and it's sometimes called a predictor corrector iterative algorithm. Basically, the idea is that suppose you have to follow a path, right? And in application, this might be, you're trying to find the root of a polynomial f of x equal to 0. And what you do is you compute another polynomial, construct another polynomial, h of t is time, 1 minus t times g of x. G of x is any polynomial you pick for which you know all its roots, usually the same degree as f plus tf. So when t is equal to 0, you have the roots of g. And when t is equal to 1, you have the roots of f. So if you know all the roots of g, you take any one of them and try to follow it as it moves in time. And typically, you take g to be x to the n minus 1. So it's a unit circle, the roots of unity. And so how do you follow a path? Well, here's a picture that you might see in textbooks. Here's a curve you're trying to follow, and you're a point on the blue point of the curve. You move on a tangent. You get to a green point, which is outside the curve. You say you move back onto the curve, take another tangent, move back, move another tangent. This is ideal. You're never on the curve. Numerically, you don't even know whether you're on the curve, right? So in reality, what you have is somewhere near the curve. You go even further from the curve. Hopefully, you come back closer to the curve, but you're still not on the curve. And then you keep doing this zigzag thing and hope for the best. And worse, if you, in certain applications, you have to make sure you don't jump from the wrong. You're trying to follow this path. But in this zigzag thing, suddenly you jump onto the second path at the bottom, and you don't know that. All right? And that's serious. Nevertheless, this is a very important method for doing roots, especially in higher dimensions. And there are softwares, Bertini, PHCPAC, Home for PS, and so on. Here's the state of the art. This is from the book of Somesi, Verschelde, and Wampler, Introduction to Numerical Algebraic Geometry. They are describing their Euler method. And look at their input. The input has the polynomial h. Now they're doing in n-dimensional, complex n-dimensional. A starting point. No, your input is this, okay, and you know that initially, so you're trying to follow the path determined by this root, x star, and then you have these parameters, epsilon, max, and min size step, max size step. All these are called what you call hyperparameters. So I'm trying to find roots. I don't care about all these things. How am I going to figure out what to give you? But you have to give the algorithm these. We don't want this kind of algorithms. In computer science, we said this is not a real algorithm. This is a heuristic, but it's not an algorithm. And maybe this is, in this day of an age of AI, we have to remind students that what AI algorithm, what you call AI algorithms are not algorithms in our sense. They're heuristics. They're very useful, very powerful heuristics, but you don't really know what you get from. You look at the output and say, oh, this looks good. Oh, so human has to decide. And a few years ago, maybe about 10 years ago, two groups of people authors came up with a way to finally guarantee that they're tracking the correct path. And it's based on Smale's alpha theory. The point, if you know about Smale's alpha theory, you know that you will have to track very close to the path. Because, and it's, in my view, is probably practically worthless in real life. And in Isaac 2018, we came out on something based on palettes test, the same palette test that I talked about in root isolation. Again, we have this notion of well-isolated disks. And this notion of well-isolated disks is much weaker than Smale's alpha criteria. And we show that you can achieve, you can take bigger steps, right, to get to the final point. And the point, very sort of a very strong property you get from using palettes test, using our soft palette test, is that now you can refine your well-isolated disk. For instance, if this circle is a well-isolated disk tracking your root, so there's no roots in a bigger circle 3 times. Suppose you say, well, I want to shrink my well-isolated test. Well, you can do a simple subdivision. You form a square, circumscribing square of your disk, split into 4 sub-squares, take the center of each sub-square, do a test, palette test on each one of these smaller circles, and you can show that each one of these smaller circles is well-isolated also, because if you take this circle and make it 3 times as big as this one, it's still inside this larger circle, so there are no roots. You don't get any new roots. So it's well isolated. And so if this test is well isolated, one of the 4 will, at least one of the 4 will succeed. So now you have shrunk your test. And this is very powerful, very powerful. Nothing like this well, I don't want to go into the geometry of good homotopy. Basically, as you track the path, let's say the path is alpha of t, it satisfies this equation, the H equation we started out with. And if you differentiate with respect to t, you get this. And now you get an expression for alpha prime, the derivative of alpha, and it's equal to g of alpha of t at t, which is this expression. And this expression, if you plug it back into this, is this very nice rational function. And basically, a good homotopy means this guy doesn't vanish. So at every point you have a direction to go. You cannot vanish. You cannot go to infinity. And this must not be 0. And now, so let's say that you're trying to track. At time ti, so I equals 0, 1, 2, 3, and so on, we have a state, which is sigma sub I. M is your current midpoint of your well-isolated disk. R is the radius of your well-isolated disk. Ti is your current time. And delta I is like, an estimate about how big a step you're going to take for the next time. It's not very critical, but you should have something like that. And if you have a state here, which is a disk, and the next state, you can take the convex hull of these things, and it forms a frustum. And this frustum, hopefully, you know that your curve comes in at this end, and you want it to come out on this end, right? So this is a valid frustum if that's true. So how do we ensure that? Well, so if you have a sequence, you may be forced to shrink this frustum, and we already saw that palettes well-isolated allows you to shrink, actually, if you want to. You shrink it so that you can get the properties you need. And so you form a funnel chain, a chain of funnels like that. This is what our algorithm will produce. And typically, people don't analyze very carefully the predictor, corrector, right? The predictor is usually not so important. You just take a step forward and hope for the best. Corrector means you have to come back to this. And this is our corrector. And notice that you come in with an expanded state, because what you hope at every step is you want to keep expanding. You want to take bigger and bigger step. You want your, I have 5 more minutes? Okay, thank you. And it turns out that you need to check several things. For instance, the first thing you ought to check is bounded. This is that you are in a good homotopy, that condition within the frustum. And if it's not, you have to go to corrector number 1 and you go out again. You have to reduce your state. But if it's yes, you go on track. On track means, is your curve coming out on the other end? If it does, then you're okay. You don't want the curve to go outside to the side. And if not, then you have corrected in a different way. And finally, you want it to be well isolated when you come out. And if not, you have to correct it. So this is the structure of our path tracker. And then, so this has a loop in there. We call the inner loop. You have to prove that it terminates. And then in path tracking, you have the outer loop. Take step, step, step. How do you know you're going to end up in the final place? That's a bit more subtle, and it affects how good your algorithm performs. So I ran out of time. I have this, what I call pathway to effective algorithms. And it's based on another paper that I worked with Su Jian from Chinese Academy of Science, where we designed an algorithm for finding roots of a zero-dimensional polynomial system with isolated real roots. And we want to find all its roots in a box. We want to certify an algorithm for that. And of course, we do subdivision. And you have predicates to test. The main predicate is, there's a predicate basically based on Jacobian test that tells you there's at most one root. And then there's another test called Miranda's test that will tell you that there at least is one root in there. It turns out Miranda test, you have to do some preconditioning called Moore-Kostelides test so that you always will succeed at some point. And then you have these predicates, and we define all this exactly using mathematical terms. I call these predicates C, the ideal one. C of any box. You have several of these predicates, but no one can implement this correctly. So we have to use interval form. So I put a box in front of C. So now you describe them as interval methods. And then effective, the interval, well, intervals have ideal endpoints. You really, in the real world, have to round it to the nearest machine representable number, maybe moving out a little bit. So you have to take all this into consideration. So the point is that at every level, you make sure that your predicate, the tilde, if this is true, it has to imply this. If this is true, it has to imply this. And at each level, you prove the correctness of your algorithm. 3 kinds of algorithms is correct. And usually, the move from one to the other is sort of minimal. Only certain things needs to be taken care of. But the structure is very clear. And I propose this is the right way to design correct, certifiable, implementable algorithms. You have to go through all these 3 steps. They're all useful. It would be very foolish if you say, I want to solve this abstract problem. I instantly go to this. Nobody will understand what you're doing because you've lost every structure when you go to machine precision. So I call this the AIE scheme, A for abstract, I for interval, E for effective. In conclusion, well, in the last 40 years, we have built up an arsenal of computational tools for algebraic computation. Basically, we now know near optimal operations for multiplication, division, GCD, now root isolation. And from now on, you can use that to build other algorithms, right? Because they are basically solved. Library, call from the library. You don't do any research on that anymore. It took us about 40 years, at least for the root isolation to come to this point. I would say for the next 40 years, to do the same for certified numerical computation, the kind of algorithms I talk about, we need an arsenal of soft tools. And basically, as I'm working on these concrete problems, I found that the tools are not there. I have to invent them, right? And I encourage those of you who are interested in algorithms to really look hard into what you do. Don't trust the algorithms you get from the libraries. They usually are just, well, it's good enough for a lot of purposes, but not good enough for certain certified computation. And the way that we uncover the needed tools is by attacking the challenging problems, a bottom-up approach to theory building. And if I look at the history of what people have tried to do in the theory of real computation, I see a lot of missteps. And that's because they're building theory from top down. And then they face the reaction of numerical analysts and say, this is nonsense. This is not what we are interested in. You're not telling anything that's of interest to us. So we want to make sure we build a theory that's actually relevant to practice. And the underlying foundations for this will follow, hopefully not prematurely, but I understand a lot of the elements that has to go into it. And there are lots of other ideas, related ideas like set value analysis, multi-valued functions, functoids or ultra arithmetic, or computing with functions. These are various groups working on different things, but they're all speaking to the same concern that I have, trying to build a theory of real computation. All right, so sorry, I went a bit over.
Thank Professor Ye for the excellent talk. So questions?
Everything is clear. All right. Yeah. Well, I think I have to use my, I think I'm fine. Yeah. Go ahead.
Thank you for the nice talk. Sorry if this question is too naive, but you mentioned trying to eliminate all hyperparameters. So one question I had is, you made choices for kind of the geometric shapes for how you would say, applying, say, pellet test or something like this. But what if I didn't pick, say, just a disk? What if I had picked a more complicated geometric object to...
No, I'm the algorithm. I designed the tools and primitives to solve your problem.
Yeah, but we could decide that we wish to tune the geometric shape. Maybe squares are better than circles, or a flower shape is better.
Okay, well, then, yeah, okay. That kind of algorithms with hooks and all kinds of parameters, hyperparameters, and but the bottom line is, at least you should have the ability to solve the problem without asking the user to give you any hyperparameters. That your solution does not depend on the hyperparameters. In our SSS framework, for instance, we allow you to choose various things actually. And one of the most important for this finding path is the search strategy. I said the search is very simple. You put all the yellow boxes back into the queue and just take out one using some priority. What priority do you use? You can use random, you can use breadth first search, you can use depth first search, Voronoi heuristics, and that greatly affects the performance of our algorithm, but does not affect the correctness.
Thank you.
Thank you for those questions. Any other questions? Okay. So thanks for Professor Ye again for his great talk.
Thank you.